Fine. So welcome to the second lecture of the machine learning and pattern recognition course. And today we'll talk about non-Bayesian methods. So first, before we talk about non-Bayesian methods, we'll go back to the Bayesian decision theory, which we dealt with in the previous lecture. And we'll talk about its limitations, despite its very broad generality, and then we'll present three formulations of the statistical decision-making problem, namely the Neyman-Pearson task, the minimax task, and the Wald task. So let's come back to the Bayesian decision theory. So we were saying in Bayesian formulation of the statistical decision problem, we say we have the following ingredients. We have the set of observations. This is something that is available to the decision maker. We were given examples of the tram where we couldn't see the number but just the make. We talked about a slot machine where the observations would be perhaps weight, radius, color, conductivity. Then there is a set K of hidden states. That set is something which we really care about. It defines the payout, but it's not directly observable or it would be very expensive. And then we have a set of decisions available. So we could, for instance, accept a coin or reject a coin, or accept a coin and assign some value to it. Now we had a statistical model of the situation. The statistical model was defined by a joint probability, and the joint probability was giving a probability or probability density. Mostly we'll be talking about probabilities because observations are, in practical measurements, are discrete. They don't have an infinite number of possibilities usually. So we had a joint probability which said how commonly a certain observation together with a certain hidden state or class appears. And then we had the loss function, which says if you make a decision for D and the true hidden state, the true class is K, how much you lose. We talked about the most, I would say, the canonical examples where the D and K are the same. You are doing classification, and if you correctly classify, your loss is 0, and if you make a mistake, either loss is 1. So it's like minimize the number of mistakes. And the strategy is how you react to an observation with what decision. So given all of that, we measure the quality of our strategy by something called risk. And you see that the risk is a function of a function. It's a functional, therefore. So Q is the decision, and it's the mean or the expected loss. Expected, you can think about it. I will slightly use these things interchangeably, but expected is the mathematical abstraction, and average would be something that we would probably see in a practical experiment with finite number of experiments. So here we are to explain Formula 1. We see that the expected risk considers all possible cases of observations and classes, and it's considering them with the probability that they appear. And what we are weighting is the loss, which depends on the K, which is the class which is not available to us, and our decision on that object. And the problem of finding a Bayesian strategy is the problem of minimizing the risk. So let's have a look at this formulation. We talked about many problems like that this formulation covers. Biometrics, fingerprint recognition, identity recognition from voice, face recognition, diagnostics, ECG, EEG, license plate recognition, dictation systems that recognize words given. some acoustic signals. So very many problems can be formulated by Bayesian as Bayesian decision problems. But already we see, if you look at carefully at Formula One, we have some weaknesses there. So first of all, this joint probability, we have two things where things can go wrong. And what it means go wrong is that if you see a problem where you cannot easily find the quantities needed, maybe they don't exist, and maybe we should not use this formulation. So, and the weakness could come both with a statistical model and related to the loss function. So here we have like three possible examples of problems. And we start with the loss function. So we said that in the Bayesian decision formulation, all mistakes are converted into a loss. We can think about it as financial loss. So you can think in Bayesian decision theory, we can say everything is about money. There are some people who believe life is like that. Everything can be bought, everything has its loss. But as a designer of such a system, one will face grave problems in the medical diagnosis tasks where maybe the price is of asking for some specific diagnosis which costs a lot or treatment which costs a lot. But if you make a mistake and don't use the treatment, the patient dies. And now, if you want to trade this off in a Bayesian setting, you would have to assign price or cost to the death of the patient, which is very difficult, if not impossible. Although in some medical systems, they try to do that. So for instance, you will say, okay, what is the cost? And what is the probability of saving the life? And then maybe there is a threshold. Then we have this example of a nuclear power plant. So this was inspired by a book by Professor Schlesinger, who is from Kiev, and he remembers very well Chernobyl. And you might have a regular inspection or replacement of some parts of a nuclear plant. And you are never sure whether the plant is in a correct safe state. Okay, okay, so fine. I wanted to mute the microphone, but wasn't necessary. So the nuclear plant might be in a safe state, and your inspections and checks and replacement of equipment is needless expenditure. So that could possibly be a wasted replacement of some part. So you have some statistical measure, you have a measurement on that part, and the part might might not be faulty. Now, okay, the cost of replacing a part which is okay is a certain amount of money, but if you don't replace a faulty part, it might be an explosion. And now, what is the cost of a nuclear explosion like Chernobyl? So first you have the cost, which means the destruction of the power plant, which is already in billions, many lives, nature, the whole thing. Actually, a massive nuclear explosion could maybe wipe out life on Earth in some worst case scenarios. Maybe actually the biggest cost of Chernobyl, I was thinking about it when I was giving the Czech lecture on Friday. What would you consider the biggest cost of the Chernobyl power plant explosion? So what came to my mind was that because of Chernobyl, Europe and many parts of the world are not ready to decarbonize economy by building nuclear power plants. So maybe if there was no Chernobyl, the whole Europe would be running on nuclear power plants. Okay, nobody knows whether that would be a good thing, but maybe in terms of carbon emissions, it surely would be it would make a big difference. But still, our original problem is we do not want to look for a cost of a nuclear plant explosion. There's no way how to reasonably set it. Another case is judicial error. So imagine you are a judge, and I think that all judicial decisions are statistical in nature. There's never full certainty. So the observation X in this case is all the evidence. Now the judge has two, let's say it's simple. The prosecutor says, okay, there's crime K, and we have a decision guilty, non-guilty. It's a simple binary decision. X is the evidence. And now let's say the judge can think about the probability of guilty given evidence, probability of not guilty given evidence. You have these expressions of like beyond reasonable doubt when it comes to things like criminal proceedings, or I don't know whether you know this expression, on the balance of probabilities. This is in civil courts, like if some damages are paid. So who knows where this is on the balance of probabilities? Probably more likely than not. Beyond reasonable doubt, maybe 1 in 1,000. Who knows? Now, but this is not what I want to talk about now. The problem is with the loss. So we have two mistakes. Someone goes to jail and he's not guilty, or you let go a person who is guilty. And now, in an optimal Bayesian setting, to balance these two, you would have to have a cost of these quite different problems. Like, what is the cost of sending someone to jail for 5 years? And what is the cost of not sending someone to jail? And they have very different impact on the society. Like, you see it now in America, all these judicial errors, which DNA testing sort of proved to, like the often conviction of black men. On the other hand, in the Czech Republic, we think sometimes that a lot of economic crimes are not punished because the judges sort of maybe don't have all the evidence, but that sort of destroys morale. So you see very different problems. So the lesson from today should be, we try to avoid giving costs to such different outcomes. So that's loss. We can have some other problems, and these are related to the statistical model. And I show this here in a case of, let's say, a military installation, which have to decide whether to shoot down a plane or not. So the decision is, on the radar, I can have only objects of two kinds: my own plane or enemy plane. And I have seen, using simulations and maybe other planes, I do know how X is the response of an enemy plane and my own plane on the radar screen. But I do not know the prior probability. Like, this example is also from the Cold War era. So there has never been an American plane, military plane, that would, for instance, appear in Czechoslovak airspace. So at that time, and trying to replace it with some random numbers like 50-50, it's nonsense. It has never happened before, and probably that such thing would start a war. Maybe it would happen only once in the history of humankind. So we have to somehow say, well, the appearance or non-appearance of an enemy plane is not a random event. Probabilities model something in reality, which in the real world repeats, and relative frequencies would converge to probabilities. So we cannot apply a mathematical model of that nature to situations which do not repeat. So still there is a statistical decision making can be formulated, because the statistics are in the conditional probabilities. Different enemy planes in different conditions will have a slightly different measurement related to them on the radar screen, but we have to get rid of probability of the event enemy plane, my plane, because there's no way to estimate and they don't exist. And the final one, we'll not talk about it too much, about the solution to this problem. It's actually called, the solution is called the Linux problem. And this is something about non-random intervention. So maybe you should remember this thing, non-random intervention, because this is the only time this appears in the whole lecture about machine learning and pattern recognition. And so far, we had only two types of, or three types of sets that were considered decide. So two decisive decisions. X was coming from the set of observation. That's what we observed. K is the class. If we knew the class, it would be easy to make decisions. Yeah? But then there is something called Z, which is not the class, not the observation. And I'll explain on the system of on this handwriting recognition problem what the non-random intervention is. So it's sort of obvious, and maybe we can look at Formula 3, that different people, different writers have different relationship between the class K and the measurement X. Everybody has a slightly different writing style. So, but now the writer, when I'm doing OCR, I don't care about the writer. It's not what I want to recover, and it's not the observation. Now, of course, I can take 100,000 writers, collect their writing styles, and learn this is a mixture model. So how would you, by the way, how you did, why, we'll talk about two things now, and now I will like some feedback from you. So I'm saying this cannot be done, why it should not be done, and why, and how would you call this probability? How would you tell someone like your secondary school's brother would ask, what is this quantity X given K? How would this describe it? Maybe you can first describe this quantity for fixed Z. If we fix Z, what would that quantity be and how does it differ from this one? And I would like you to understand this process which is described by Formula 3. Anyone wants to say something on this?
Maybe the a P of X given K is like a general term, and P of X given K and Z is like more specific for some specific type of writer, for example.
So the one Px given X and Z, if Z is a constant, this
Yes,
is
right.
what is the distribution of observations for a given writer, one given writer. And this is some sort of like average writers writing of letter K. Yeah. The problem is that the user is not an average writer; it's one user, and people really write differently. So if you design a right OCR system based on this probability, and you declare on the product, on the box, I have less than 1% error, then this will be true for some users, and for some other, they might have very high recognition errors. So how many, about half of the students listening are Czech. And we have been we collaborated with Pilsen University, who are doing speech recognition, automatic speech recognition. And they do it for all transmission from the Czech parliament. And some ladies, and I remember top was this lady, Němcová, who now wants to be a senator in Prague. She had 99.5 recognition rate on word level in Czech because she speaks slowly and very nicely pronounces everything. And there is one member of parliament who had only 43% recognition rate. I guess the Czech guys know who it was. Do they? Who do you think was the one who had the worst recognition rate?
Schwarzenberg?
Exactly. He had only 43%. This is a guy who grew up in Austria, speaks with a strange way, had some sort of speech impediment. So it's very difficult to deal with this problem because every person has a different one, different probability, and you cannot mix it because it's, of course, this would be appropriate if random people were using randomly or OCR, and there would be switching. But why this is called non-random intervention? Because once you buy the software, you fix the Z, and you would like it to work for your Z, and you don't care about the average. You care about your one. I will come back a little bit to this prior probabilities, another situation where they exist, but it's quite inconvenient. So in the Czech Republic, the license plates of a car depend on your location. So the first letter in the license plate defines your region. In Prague it's A, in Brno it's B, and so on. So if you are doing a license plate recognition system, the probability of the first letter differs with every location. So maybe in Prague it will be dominated by A with a little bit of S, and which is central Bohemian region, and somewhere in Moravia it will be Z and T and N. So it is possible to, let's say, install your system for license plate recognition in a tunnel in Ostrava and have it estimate the probability of the first letter there, but it's extremely inconvenient. So in principle, you could estimate the probability of K, where K would be here any particular license plate. You can estimate that, but it's extremely inconvenient. So it's much better to have a system whose performance does not depend on the PK, which is for the license plate in the Czech Republic, they are a function of location. Yeah. Okay, maybe this is the end of the introduction. Any questions to the introduction? Because now what we'll do, we'll talk about 3 ways of formulating the problem, statistical decision-making problem, that avoids the use of costs and prior probabilities. So the lesson is, if somehow the problem that you are studying, where the application does not fit the framework of Bayesian decision theory, go and use something else. It is possible. Any questions to this part? By the way, you can also write things in the chat. I'm following the chat. So it might be simpler. So fine. It seems there's no problem. So the first formulation will be name and Pearson task. Most of you know it, and I'm not sure you would recognize it as such, because this is often referred to as hypothesis testing in statistics. So, and we'll cover the task only for 2 hidden states or 2 classes. And to like make the terminology easy to remember, I will call these 2 states or classes dangerous state and normal state. So maybe you can think about an incoming airplane as in normal state if it's your airplane, or dangerous for enemy's warplane. You'll see that the dangerous state is the one that gets special treatment. You'll see that you deal with it in a different way, and you control more what happens with objects of that state. We have still observation, and the only thing we need is, from a statistical point of view, we need the conditional probabilities, probability of X given dangerous state and probability of X given normal. The priors are unknown or do not exist. So an example of such situation could be that you are trying to test a pill for weight reduction. And what you'll do, you will test it by administering placebo to some people and the pill to other people, and the X will be the difference in weight in 1 month. So for one state, you expect that if you are administering placebo, roughly speaking, you don't expect any change in weight in 1 month, but a significant one. So you expect something with 0 variance. and for the treatment, for the effective pill, you expect some weight reduction, which will be quite important. But you do not want, you want to avoid all sorts of costs associated with mistakes for decisions. So the Neyman-Pearson tasks looks for an optimal strategy, which is defined in the following way. It must, an acceptable strategy must make sure that the error of classification of the dangerous state is lower than a predefined threshold epsilon d, which is something that the user has to provide. And given that the error of the classification of the dangerous state is lower than epsilon d, the classification error for the normal state is as low as possible. So you can see that the dangerous state is the one which is important. You say the error on that state or for that class will be controlled as well as you wish. You can put epsilon d to 1%, 2%, and the error on the other state will be whatever the minimization can achieve. So now here is the formulation mathematically. And one thing which I think is important for today, that you leave the lecture while understanding, at least understanding what is written here. That itself is a little bit of a challenge, at least that's my experience with students. So you see, this is a constraint optimization problem. And maybe we speak about a constraint here. So what is this sum? So we are saying, okay, we have a dangerous object, and that dangerous object can generate some observations. If we summed over all x, that would be 1 because it's a probability distribution. But we are summing over x, which are actually classified as not dangerous. Yeah. So if x is generated from a dangerous object or dangerous class, and it's not classified as such, it's a mistake. And if we sum up the probability of all such mistakes, that's the missed, it's something can be called missed dangers, overlooked danger. And that's exactly what we have to control and keep below epsilon d as the user requires. And then given this constraint, we are trying to minimize the error of the other class on the normal class. So again, the normal object can generate various x. And if we make a mistake, if we classify such x as not normal, which means dangerous, and this is the mistake on the normal object, and it can be called false alarm because this is the sum of cases from the percentage of the normal object cases which will be classified as dangerous. So questions about formulae 4 and 5. Any questions? Is it clear, or if you ask now, maybe we'll come back to it later. No questions. Okay, nothing in the chat. You're doing well. Fine.
Hi, I just want to make sure that I understand it. So the idea is that, so kind of the important part is the subject to right here, right? So the idea is we want to minimize the error with respect to the normal class only insofar as we've already minimized the error with respect to the dangerous class.
I think you get it right, but you say it wrong. You cannot minimize two things because they are contradictory. You can constrain the mistake on the dangerous class,
right?
And once you satisfy that constraint, you want to minimize the other.
Right. Oh, okay. Okay.
So, and now the first question would be: is there a solution always to this problem? So let's say I put epsilon d for some problem. If you remember, okay, I can switch to the other camera and show an example something that we'll deal with later. Where is it? Here. So maybe imagine that you would like to distinguish between men and women on the basis of one single scalar variable. So let's say this is weight, and this would be the distribution of, or maybe weights of man, and this would, and women are in general slightly lighter, so we do something like this. So this would be px given woman, and this would be px given man. And you see the two distributions overlap quite heavily. So it seems that it's difficult to have a good classifier, but can we still satisfy a Nijman-Pearson formulation where we say that, let's say we choose the women to be the dangerous class, and we say, well, I want a mistake, the error on the female class to be less than 1%. Can we satisfy that? Can we satisfy? So does this constraint optimization solution, does it have a solution for any choice of epsilon d?
Yes, it does.
Why?
Because we can classify everything as the dangerous class.
Exactly. So you will be shouting false alarms all the time, but it is, you can always satisfy that. So now you see that if we have two classes, which can be, you know, in statistics, we often call this two hypotheses, two states of nature. Like the language, somehow slightly different language would be used in different settings. Naturally, we have two mistakes. One is the false alarm, and the second one is the overlooked danger. In Bayesian settings, they will get a cost associated with these two, and will minimize their weighted sum. Now, whereas here we are saying, no, we don't want to do that, because first of all, we don't know how often they'll happen, yeah? Because if someone says how often the false alarm happens, it's not this number. This is, if an object is dangerous, here, this one, 7. Overlook danger. If the object is dangerous, how often do I classify it as non-dangerous? But if, for instance, a dangerous object never appears, so for tens of years, the Soviet defense system was monitoring all the airplanes around, and it never overlooked the danger, because never in the 25 years a military airplane, let's say enemy military airplane, ever entered Soviet airspace. So this is the probability of a dangerous thing to be overlooked. It's not the probability that an object arriving is dangerous, because if something never happens, you will never observe it. Okay, so now we'll just show this example problem on which we'll show the solution. So now at the moment, you are in a state where you understand the Nijman-Pearson formulation. Then you need to know the solution, and those who want to be completely happy, they also know the proof of the solution. Then you know everything. Yeah, of course, because we already introduced two problems, Bayesian decision making and Nijman-Pearson, we see that different situations might require different formulation. So our problem is this: an aging student at CTU wants to marry. He can't afford to miss recognizing a girl when he meets her. Therefore, he sets a threshold on female classification error as 20%. At the same time, he wants to minimize misclassifying boys for girls. So he doesn't want to, he has probably also weak eyesight, so he approaches a lot of people, but he says, okay, they are so rare, these nice girls here, that I want to put it to 20%. So the formulation is, K is dangerous, normal, female, male. It's not, this doesn't mean that females are dangerous. It means this is the class where the error of mistakenly classifying F as M will be controlled. It will have to be less than 20%. The measurements will be 2 measurements will be available. And so the space of observation is Cartesian product of short, normal, tall, this is height, and ultralight, light, average, heavy for weight. We do not know the prior probabilities. The guy might be doing it once at the underground station, one at a, I don't know, school for nurses, once for at FEL, where we have only something like 13% of ladies. And the conditions are given as follows. So you see that females are mainly 30% of females are light and normal. It's very, very unusual. 1% of ladies are tall and ultralight. Men are often average and normal. Some of them are tall and average, and some are tall and heavy. Whereas we are saying here there are no tall and heavy ladies. Okay, so now this is the statistical model. And here, notice we don't need any prior probabilities. We do not need any costs of making mistakes. It's all to know these priors, and these can be reasonably established for any location in the country or maybe in Europe, roughly speaking. You do not, they are sort of, we can think about them as universal. So now the solution, and I will now first define it as a result, and then we'll talk about how it came about. So this result is called Neyman-Pearson lemma. And it says, the optimal strategy depends on the likelihood ratio. There is a constant mu, and given this mu, an optimal strategy. What is the optimal strategy? Is the one that satisfies the constraint and minimizes the false alarms. It is such. For any x, get this likelihood ratio, and if the likelihood ratio of normal divided by dangerous is above a threshold, decide for normal, and if the likelihood ratio is below, go for danger. The optimal strategy requires to find a mu, and how this is done, because the thresholding, you have to threshold the likelihood ratio. If you know you have to threshold the likelihood ratio, you can start by saying, let's put the threshold to, now let's see if it's smaller than something. So you can start from 0 and then go up and up and up. And as you are deciding for more and more normal class results, you will soon reach this threshold, and that's where you set that's where you finish your process. So we can look at our numerical example. We get this ratio. So for every possible measurement outcome, we have only 12 possible measurement outcomes. We calculate the ratio of male over female conditional probabilities is calculated. And here we have infinitive. This is because the females have 0 probability of being tall and average or heavy, according to our table. So because we'll be thresholding, it's enough to actually consider ranking of these measurement pairs. And we'll see that if we could, it will be, I actually said it the other way around for this example. We'll start from the top and say, okay, we'll be deciding for males for the highest likelihood ratio of male over female. And we'll be counting the probability of females being counted as males, which is overlooked danger, and that must not be more than 20%. So if we take the mu at above 2814, this will put these two boxes tall average and tall heavy to be classified as females. That produces a 0 error because no females are in these two boxes, and the error on males will be 0.57. So we satisfy the constraint, overlook danger less than 20%, but we are not yet in the optimal point. So we can also add another, reduce the threshold, for instance, to 0 to 2.5. So we go from top to bottom, and we see that then the first thing that's added here is that number 10 cell becomes classification as females, and that means that the error on females will grow by 14%, and the male error will drop because now the 3 green cells will be correctly classified. So we already are at error which is lower, and it's 16%. Okay, maybe we can go further. So the next cell is the one with 2.2 threshold, 2.2 ratio. Females have gone up to 16%. This cell here, 0.17 has been added. Males are down to 13%. And if we look at the whole situation, as we are adding the box number 10, 9, 8, 7, these are ranks. We took every pair of observations and ranked it by the ratio. The error on males is dropping because more and more measurements lead to decision males. The error on females is growing, and we have to stop the threshold at before we reach the 20% decision boundary. So, and the optimum for such strategy here would be 0.18, so 18% for females and 10% on males, and that corresponds to something between any threshold between the ratio in cell 5 and 6 will give this result. Yeah. So for instance, we could get the mu in the middle between the two. Okay, who got the idea? Seems you are nodding. I forgot to switch to the camera. Maybe by far the most important thing here. What we see, I will now I will go to the paper, and if you can easily verify, and you probably will do it in the lab, what we are thresholding is not the x-axis, or you can even see here we have x and y, we have two-dimensional distributions. We are not thresholding the x, we are thresholding the likelihood ratio. So for instance, if we have two distributions, one like this, and the second distribution is something like that. These are conditional probabilities. So this would be px given, for instance, dangerous, and this would be px. The blue one would be px normal. The decision function would look something like this. Perhaps here we would be deciding for dangerous. In here it will be normal. Somewhere here it will be dangerous, and normal and dangerous again, because you see that these the ratio here, we have px of given d is a constant function, so the ratio is this sawtooth function, And therefore, some threshold will be thresholding on this, on the ratio, because the blue thing is also the ratio, especially if, for instance, this is 0 and this would be 0.1, then px would be equal to 1 as a constant. Yeah. So I'm actually here showing this would be the probability densities, because I'm sort of drawing it as a continuous variable. So the important thing is to remember we thresholded the ratio, not x. This example is misleading. It's dangerous. Yeah, I'll put here two, because here, as it happens, the ratio of x, px given, and we did normal to px dangerous, is monotonic. So it looks like this. Actually, this would be log of the ratio. Log would be linear. So if we are thresholding a ratio, we can threshold any monotonic transformation. So if we had e to minus x minus a squared here, and here it would be e minus some x minus b squared, you can show that for these two normal distributions, the logarithm of the ratio is a monotonic function. So thresholding here, as I said, we threshold on the ratio. This is the ratio, is the same thing as thresholding on x, but this is a special case. And we have, so remember that we threshold on the ratio, not on some measurement. Probably with this two-dimensional example, it will never come to your, you will never have this idea, because we have a two-dimensional discrete thing. So the ratio sorts out our measurements, and that's what we threshold. So that's, the bottom is the right thing. The top one is a special case where where some monotonic transformation of the ratio is a linear function. Therefore, thresholding ratio means thresholding the x. Yeah. And also maybe one more thing I will speak about, what in statistics, or at least maybe this is maybe not for professionals, but this is something that really sort of made me curious. Like they said, well, okay, we have one-sided and double-sided tests. So if you have a distribution like that, and the ratio, so the important thing is that the ratio r of x is, or some monotonic function is linear, your optimal solution will mean that your decision function will be blue here on one side and red on the other. Yeah. So this, what they would call this, we are building a one-sided test. And then they say, well, but sometimes we want a two-sided test. And that would be for the case where we have one distribution like this and another one is more peaky. And the ratio here is a quadratic function. So you will say something like this, blue in the middle and red on the two sides. Yeah. Red here and red there. But as we saw before, you can have many other different setups, like for this sawtooth pattern, you can have class 1, class 2, class 1, class 2, class 1. So the two cases which are often covered in statistics are like very special cases where you have a monotonic or quadratic, well, log quadratic, like log is quadratic, it doesn't ratio. So people, I was always confused why there are only one-sided and two-sided tests. There could be actually many other. So and what you call significance is overlook danger, because the significance is something that you have on the under control. So the null hypothesis would here be the dangerous one, because that's the one where you say, okay, I want to reject the null hypothesis with a if it's correct only with a controlled percentage. So that's the case here. This is the dangerous one. The dangerous, I have to control the error, and the other error, which we called here false alarm, that would be power of the test in the language of statistics. This power and significance, to me, these are not names which would help you to understand the concept. Yeah. So I will now go back to the slides, and I'll switch the camera. Okay. So let's go back here. I will skip these examples, and now we have the proof. But before we go to the proof, let's talk about what you heard so far. So are there any questions? I see nothing in the chat. Any questions?
Yes, I have a question.
Yes.
In the example that you were showing, I did not understand how you were choosing there, in what range constant mu should be.
Well, the mu could be, so, okay. So okay, I can use the slide that you can see now. So the likelihood ratio, so first of all, these P are probabilities or probability densities, depending on whether P is discrete or continuous. But the form is exactly the same. So these are positive quantities, okay, no negative. So they will never be negative. It could go to infinity. So it's between 0 and infinity. It's possible that for some x, the normal state never generates that x. And it's possible that for some x, the dangerous state never generates it. So it's between 0 and infinity. And in this, yeah, so you can start from infinity and go down. Is this answering the question? Yeah, good. Okay, I saw the thumbs up, which hopefully means okay.
Yeah, I just understood what it means they are. And it's good. I got it.
Okay, good. Good. So now the proof. Why? I'm not sure how far you are in optimization, but there is this magical thing how you solve constraint optimization that okay, we'll make things a little bit simpler by saying that the formulation was with an inequality. We were saying, well, the overlooked danger must be smaller than the required epsilon d, but it's sort of obvious that the optimum one will be exactly attaining the required border value. So we'll treat it as a constraint optimization with equality constraint. And then there is this magical Lagrangian multiplier. You say, well, I will add my constraint, sort of add a constraint to the formulation with the mu, which is the Lagrange multiplier. And now let's have a look at this formula, and we'll express this is normal. So this thing is false alarm, and we'll express the false alarm via a sum over the x where the normal outcome is the decision. So we said, well, overlooked, false alarm is 1 minus correctly classified normal object. And now we see that the sum are over the same domain, over all x's where we decide for normal. So we can then put these quantities inside the same sum. And now let's think about equation 16 and this t of x. Now, no matter what mu is, so you can think someone sets mu, the Lagrangian multiplier value, no matter what the mu is, if we look at this sum, for any x, we can either have the x in the sum, which means you decide for as normal that x, or you can decide x as dangerous, and then it's not in this sum. So when will you decide for, when do you want to keep this expression, which is called tx, inside the sum? When it's negative, because this is your loss. So if t of x is negative, make the decision normal. If it's positive, make the decision dangerous, because by removing a positive part of this sum, you reduce the loss function. So no matter, so if tx is positive, we decide for dangerous. If it's negative, we decide for normal, because it's in the sum, it reduces the loss function. But now, when is tx negative? Well, when this thing is negative, but when is this negative? Exactly, well, for every mu, it will be a different value, but no matter what mu, there will, for each mu, it will always depend on the threshold. Yeah, so if you ask, when is tx greater than 0? Well, when mu times px given d minus qx given n is greater than 0, and then you do the simple operation and you get exactly this result. So this formulation with the 16 shows that the decision must depend on the quantity tx being negative or positive, and that's exactly the same as thresholding. And we don't know what the mu is, but we know that if we threshold, we can go in, when we go for, if with likelihood ratio is defined as px given n over px given d, we can go from the top, from infinity, and when we reach the position where the epsilon d is reached, we stop, and that's the mu. So now we have some sort of a problem. Okay, I was saying that we have this equality constraint, and but we noticed that in this previous example that we worked on, the error on women was 0.18. So we did not reach the error 0.2. Now, if we added, so we had here, the decision is up to 6. If we add the bin number 5, we can't do that, because we see that that's 30% of women, and that would be way over the threshold. Does anyone have an idea how we can reach exactly 20% error on females and reduce this epsilon m? Any idea?
We'd have to add more classes or more bins, right?
That's one thing, but correct. But at the moment, we have exactly those measurements. So if we had more classes, then it would be possible. And of course, in the continuous case, this type of thing cannot happen, because there will always be the right threshold where exactly we reach this epsilon f, which is allowed. But maybe for this particular example, we have no other measurement. We still want to improve on this result.
We can change the probability of men to women, and then this.
No, this is like a triple fault.
Like the already known kind of on the plate.
This is a triple fault. First of all, we don't speak about prior probabilities. This is a solution where we have no probability of prior for men and women. And second, we can't, like the distribution, we don't want to, I don't know what, feed women more or feed them less so that the distributions open up. Yeah. So no, that's not. We can still do it with exactly this statistical model.
We can do it using other brackets. For example, we can see that females are not usually tall and light. So we can add a little bit of error if we say, okay, that's...
Maybe you are going the right way, but I will say it formally. If in bin 5, we decide 10% for females and 90% for males, 90% for females and 10% for males, we only add 10% of this to the false, to the overlooked danger. So we can introduce a randomized strategy here. Yeah. So now we didn't have time to do that in the lecture, but it's in Bayesian decision making, randomization has no space. It's always suboptimal. Whereas here you can randomize and say, if measurement 5 appears, 95% will be women, 5% men. And through that randomization, you can actually go exactly to this point where you intersect 20%, because you will be misclassifying not all the females, but only 95% or 90%. So actually we can calculate it. So we can still make a 1.2% error. So we see that this is 29. So the 1.2 over 20, it's 0.12 over 299 is the probability with which you can go for women. Okay, so that's this. We can derive this as a linear programming problem. I'll skip this. And this is the randomized strategy that we just covered. Maybe this is a simpler one where it's obvious, more obvious how to achieve exactly the right allowed error on the dangerous class. Okay. One thing. By the way, this is probably the oldest formulation of a statistical decision-making problem. It can be generalized to more dangerous states because you can add more constraints. And the only thing you actually need to know is this ratio, the likelihood ratio. Okay, this is an interesting example, which is very interesting in medical cases. So imagine that, come back to this, let's come back to the weight reduction pill, and we want to introduce it to the market, and we are testing. Now, let's say that the blue thing is, you see, it's the dangerous class because that's the one we want to control, but it will be the null hypothesis. We are saying, this is what happens with weight of people who are given placebo, who are not given the pill. Their weight changes because of random effects, but on average, it's no change, mu 0. If I administer the pill, the weight will now drop to mu 1 on average, but the people will also have these random variations. When I'm testing the pill, I do not know at all the statistical model. I don't even know how will the red thing is the weight of people after 1 month eating the pill. But I don't know the effect. But I can still set up solve the Neumann-Pearson task, because since the likelihood ratio is monotonic, I know that I'll be thresholding on X, and this overlooked danger must be only 2%, and that depends only on the blue curve. So I can say, well, I will accept the pill as effective if the weight of my patients after admission will be below X threshold, and I will make a 2% overlooked danger error, which means with only 2%, I will accept the pill if it's actually not effective. So this is very nice, because if the red curve was 100 kilometers to the left, the solution of the Neumann-Pearson problem would be exactly the same, X threshold. I don't need to know. I just need to know that the likelihood ratio is monotonic. Therefore, it will be a threshold on X. And then the threshold itself is defined by this integral from the tail because that's are the incorrectly classified normal cases. Questions, or is it clear?
So the significance level of this example would be like 98% because we are only allowing
Yeah.
Okay.
Oh, yes, exactly. Yeah. You will say like with 2% I will accept something which is not working. That's fine, the 2%. And to do that, I need not know. Of course, depending on the sigma, I could like do the other mistake. It's actually the other mistake is the pill is effective, but by coincidence I got someone who by random chances end up somewhere around mu0, and I can reject the pill actually when it's effective. But that will not be under control. The only thing I want to do is not to accept the pill if in fact nothing is happening. Okay. Second formulation. Now, there's one thing which is not nice in the minimax, in the Neyman-Pearson task, that's the fact that we had to treat the two classes differently. One type of error was special and the other wasn't. So in minimax task, we treat all classes equally. So now we'll formulate it for n classes. We'll have again some set of observations. We assume that the conditionals are known. So we know the observation distribution for a given class, and we do not know the PK or they do not exist. That might be both cases. So maybe the case with license plate recognition would be the case where they are unknown because it's inconvenient to try to install and then measure for a long time the probabilities. And now, so the optimum strategy from the minimax point of view, it minimizes the classification of the worst classified class. Now, maybe that's difficult to understand, so we have to spend a little of time on that. So if we have, let's say we have n classes, and we have a space of observations X. Maybe I will need to draw something. Let's see, let me switch here to the camera. Okay. So imagine we are measuring weight and height. So this is our space X. And we are interested in large mammals in Africa. And maybe something super heavy and big is an elephant. So that would be class 1, say. Yeah. So, okay, now we have to be careful. Now, of course, elephants have a distribution. And but we would like to find a space of observation, which we'll call X1, because elephants are class 1, where we decide for elephant. Something which is not so tall, but very heavy. Maybe this is a hippo somewhere here. This will be our, so if we make these observations, we'll decide for hippo. Maybe somewhere there will be a zebra here, or zebra, depending when you are from Britain or America. And maybe the last part will be, so something tall and quite heavy, this would be a giraffe. Okay, so, well, this is, okay, so no, giraffe will be F. Yeah, so this is F. So this would, now, of course, we start with statistical models. Maybe giraffes have, or zebras have this type of distribution. There are densities around here. And what I showed here is the decision space. But now, what is the probability of making an error on elephant? Yeah, this is class K. The probability, so if we take all elephants and see all the measurements they can generate, and we sum up all these or integrate, it depends on the probability density, but sum up, normally we'll have discrete measurements, over all x's where we decide for other classes, That's the error on the elephant class. So to get the error on the elephant class, we calculate that the probability that elephant falls into this dashed area. What is the probability on giraffes? Is the probability that the giraffe, which might have some sort of a distribution like this, that the observation taken on a giraffe will fall into the other areas. There's a probability on giraffes, and so on. So every class in general can have a different error. So for instance, if someone is crazy about giraffes and everything, they see an animal and say, this is a giraffe, on the giraffe class, we will have no error because every giraffe will be classified as giraffes, but some elephants will be giraffes and some zebras will be giraffes and so on. Please, who understands Formula 28, like the error on class K? And the formula, you can say something here and type a message in the chat. And now, yeah, good. So I see the thumbs up, that's good. So now, and the formulation is, I do not want to have a class where I am actually making many mistakes. I will measure the quality of my algorithm by the error on the largest class. On the class where I make the largest number of errors. Yeah. So it's clear, for instance, that in a two-class problem, in a continuous space, the errors must be the same, yeah? Because if you have too many errors on one, you can reduce it so that you make more errors on the other. Because as you are making more decisions into one class, you reduce the error there and increase in the other. Okay. So again, you would have to do the derivation again via linear programming. But the main result, the only result I'll tell you is that, okay, before I'll say the formula result, let's have a look at the example that we had before. So before, we wanted to have 20% on females and whatever came out on males. Now, you see that if we threshold on different bins now, we see that the min-max error, we try to minimize the upper error. So here you have more errors on females, here you have more errors on males, and this is the global minimum. So we can prove that, again, the optimal strategy is based on the likelihood ratio. So only the ranking of the bins is important, but this time we do not guarantee anything for any class. We say minimize the case of the worst class, and we get somewhere here. The error on females is 16 and on males is 13%. And through randomization, you can make these the same. Yeah. So if you think about it also, okay, there, like maybe I'll, now there's one more problem, which is exactly the same solution, but it's a different one. So in the minimax setting, we didn't speak about prior probabilities. Yeah, in here, we just say, okay, only conditional probabilities appear in the formulation. But there is a different problem where we say, okay, there are prior probabilities, but we do not know them. That's maybe the case about license plates. Or actually, we come to another park and we do not know the number of elephants and giraffes and hippos and zebras in this park. We don't know the priors. They will be different in different parks. We do know the heights and weights of certain species of elephants and giraffes, but we don't know the priors. But they do exist. And let's have a look at one way of writing the error for Bayesian formulation. Well, one way to write the error is go for all examples, x and y, but count only those where the x and k count those examples where the decision is incorrect. This joint probability can be expressed as product of prior times conditional. The P, this is a function, the sum is over X, so we can take the PK out of the summation. And we see the error, and this is when people see this, if you show this to some secondary school student, he will not understand at all. But if you say what it expresses, it's obvious. The error of my system is the average of errors for various classes, and it gets the weight, which is the prior probability of the class. Yeah. So this is something like you can say, well, if I have, I will be examined on examples from 3 types of subjects, and in one there will be 20% from one, 80%, 60% from other, and 20% from the third subject. And this is the probability I'll make an error in that subject. This will be my overall error rate. Now, if you look at this 29 formulation, this sum is something called a convex combination. PK is a sum of these are numbers which sum up to 1, and they are non-negative. So think about if you have epsilon k, the errors for the different class. What is the worst case for this type of system? Well, the worst case is if I'm examined on the core subjects where I know worse, and then my error will be exactly the worst error. So the worst case scenario here is that we are only shown examples from the class which we make most mistakes. But if this epsilon k is the same, then no matter what pk is, we have the same error, which is actually exactly epsilon k. So we see that this Bayesian problem has the same solution as the non-Bayesian problem, and because the minimax solution is insensitive to the priors of given classes. Okay, so fine. For 2 classes, it's actually exactly the solution is as easy as for the Nijman-Pearson task. Calculate the ratio and find the decision such that you find this point, and below you decide for one class, and for the other, and above it's the other, and that's it. Final thing I will talk today is Wald's task, and it's a different generalization of the. You can think about it as generalization of the Nijman-Pearson task. So in Nijman-Pearson task, maybe we would like, and some students suggest that we would like to set the threshold on classification of both classes. We would like to have an error on the first class, an error on the second class below epsilon. Now, if we go back to this example that we looked at before, say here, it's obvious that if someone wants to decide between men and women based on height only, with error 0.5%, it will not be possible. It's impossible. So we cannot require these 2 constraints because we will end up often with no feasible solution. But what we could do is to introduce a do not know decision. This is very similar. If you remember, we had a Bayesian decision making with reject option, where we assigned cost to saying I don't know. So I don't know was you got some penalty, less than being wrong, but more than being right. But now we do not want to punish errors by losses because we do not know how common various things are. But we could still say, okay, start like with Nijman-Pearson, calculate the error for class 1, keep it under control, keep under control the second error. We have these two errors. And at the same time, minimize how often you say, I don't know for class 1 and I don't know for class 2. So this is always solution because for any epsilon, you can always say, I don't know all the time. So you can solve it. Yeah? So the solution is, for both classes, make sure the errors are less than epsilon. And at the same time, minimize the maximum of kappa I. So what was kappa I? So you, that was the probability of saying I don't know on the first class, and kappa 2 is the probability of saying I don't know for class 2. Now, question. Okay, here. Question. Why do I have max here in formula 34 and not sum? Why don't I try to minimize the probability of saying I don't know over all classes, so to speak?
Oh, well, because like you said, you can't minimize two different parameters at the same time.
No, because we are minimizing just one thing. Here these are constraints, and we could be minimizing max or sum. Formally, it's not a problem to replace max with sum. That's one real number. If you have k numbers and you sum them up, you get one real number that can be minimized. If you have max, given a set of numbers, this is also one real number and that can be minimized. So that's not a problem. That's a different one.
Maybe we make sure that the value we choose gives us the maximum or the most optimal outcome for the optimum Q.
So there are some people who say people should be killed for saying most optimal because optimal is already optimal is the best thing. But why? You can say it's optimal. Okay, these are two different optimality criteria. Someone might want to care about not making a lot of errors for the worst class. This is max, and someone should say what would like to say, yeah, but I care about the total number of I don't knows. Why you can't say sum? What is the problem with it of saying I would like to sum the I don't knows? Maybe this is very difficult.
Because they represent some kind of error or uncertainty.
No, yes, but what? So if I was examining a student from two subjects, I can say, well, okay, so fine, I will give you 10 questions, and you have you have to have you will pass if you make less than 1%, one error on each of the subjects, and all in all, you can say 3 times I don't know. Whereas this one, I say, well, behave in a way that you say I don't know. You control the number of I don't knows in each subject, and at the same time, your errors must be below the threshold.
Because then you don't know who made which error, basically.
Okay, the problem is that you don't know the prior probability. Yeah? So if someone says, I would like to do the sum is meaningless. Because if you, so imagine that I can choose eight questions or 8 objects from one class and 2 from the other, and it could be also the other way around. So if you make many more I don't know answers for one class, your result will depend on the prior probability that an object of that class appears. So the max ki does not depend on the prior probability of the class, whereas sum of ki depends if the ki's are not kappa i's are not the same. Sorry, kappa i's. Okay, and then the interesting thing again. So you see, for 2 classes, the likelihood ratio is an extremely important quantity because the solution is actually a mixture of like, it's like two Neyman-Pearson problems where they swap the roles. So if the likelihood ratio is high, above mu, okay, high above mu h, you go for class 1. If the ratio is very low, you go for class 2, and in between you say I don't know. And you can imagine that this you set the mu L and mu H exactly like we did it in the Neyman-Pearson problem, because we started like, so we start from say infinity and start going down until we reach a position where the error on the class 2 has reached the limit. Then we start from 0 and go up, deciding for class 2 until the error on class 1 has reached the limit. And whatever is in between, you have to say don't know. And that's the optimal solution for this Waltz problem. So the Waltz problem is interesting in that it teaches you when to say I don't know. We'll touch the Waltz. The name of the Waltz, which Abraham Waltz was a very is an eminent statistician, and he was like the father of sequential decision making. Because imagine that you are a doctor and you have available some test results of some diagnosis. So for testing, so some blood sample, and it's obvious. You could say healthy. It's obvious the other way around. Very low percentage of the virus. You say healthy. A high percentage. You say dangerous. And in the meantime, in the middle, you say I don't know, which would in doctor's practice, he would not say I don't know what's wrong with you. He will order you to get another test, so the X will change, and then he can do it again. So it's sort of a preparation as well for sequential decision making. And here, for instance, if you want to make a 5% error on this problem of males and females according to this table, you see you will be saying, I don't know a lot. So in 50% of cases on males and almost 50% of cases on females, you will be saying, I don't know. And funny enough, the solution produces 3% error on males, 0 on females. Through this randomization trick, you get slightly change it so that you reach exactly the 5% on both males and females, but we didn't work it out here. Okay, so we are just on time. Questions?
Why was it set to infinity, like those two?
Because we are dividing px given m, which is, for instance, over px given f, and that was 0. That's 0. Yeah, if you look here, you see that in our statistical model, it happened that we postulated that there are no tall and heavy women. So when you divide these two numbers, you get infinity.
Okay, it's because of the ratio. Okay,
but it doesn't matter, because that what immediately you will decide that these two 11 and 12 will be classified as women. That's no error there. Yeah, we can have like 10 to infinity or whatever. Okay, no more questions. Fine. Okay, so maybe I can switch it. And fine. So that's lecture number 2. Thank you for listening, and see you next week.
Thank you.
Goodbye. Thanks.
Bye-bye.
Bye.